Okay, I've changed the board, and now I'm ready to talk about conservation of energy. I'm sorry, conservation of momentum. So I've developed the impulse momentum theorem, and it's up here, and it says that the net force applied on an object times the time the force is applied is equal to the change in momentum of the object. The same thing as impulse. Okay, now if we divide both sides of this by delta t, we've isolated the force. And the sum of the forces on an object is equal to the object's change in momentum divided by the time required to make that change in the momentum. And that, by the way, is really the original way that Newton wrote the second law, not F equals ma. He wrote it as the net force acting on an object is equal to the time rate of change of the object's momentum. Okay, now, having said that, if the sum of these forces is zero, so if this is zero, then that necessarily means that the change in momentum of the object will be zero as well, right? If F here is zero, then that absolutely ensures that the change in the momentum must be zero. So that's what I've got down here. Now, if the change in momentum is zero, that means that the final minus the initial momentum is zero, so the momentum doesn't change of the object. So you can write that like this. Final momentum is equal to initial momentum, and by the way, that is conservation of momentum. Momentum remains the same, it's conserved. And that's true for an isolated system, a system where the outside forces are not, there are no outside forces acting on the object. And now I've got an example problem that involves that idea of conservation of momentum. And it's a collision problem. Most conservation of momentum problems involve collisions or explosions or something like that. So here's an example problem. You've got two boxcars. The first one here on the left, boxcar A, has a mass of 10 to the third kilograms, and it's moving at a speed of 10 meters per second. And remember, momentum is mass times velocity, so we could easily calculate the momentum of this boxcar now. And it's headed to the right, and it's going to run into this boxcar, which is much heavier. It's 4 times as heavy, 4 times 10 to the third kilograms. It's boxcar B. It's moving at only 5 meters per second. It's moving half as fast, so it's going to get rear-ended by boxcar A. So here's the crash. So picture 1 before the collision, picture 2 after the collision. Here they are. They're moving off in tandem now, connected to each other, and they're moving off with some final speed, v final. And we want to solve for that final speed. We're going to use conservation of momentum to do that. So here's conservation of momentum. The initial momentum is equal to the final momentum. We can calculate the initial momentum of this 2-car system by multiplying the mass times the velocity of one car and adding to it the mass times the velocity of the other car. And if we do that, we get 3 times 10 to the 4th kilograms per meter per second. Yeah, okay, so that's 30,000 kilograms meters per second, and the units for momentum are mass units times velocity units. There's no special name for them, just kilograms meters per second. So now that's the initial momentum, and if the momentum is conserved, that means the momentum before the collision of the two objects is equal to the momentum after collision. So the momentum after collision is equal to the mass of the now basically one object moving off at this, it's connected now. So that's going to be the 10 to the third kilograms plus 4 times 10 to the third kilograms, which would be 5 times 10 to the third kilograms, times the unknown final velocity, v final. So now disregard this stuff over here. Come down this way. We're going to plug in the value for the final, or for the initial momentum using initial equals final. So that's 3 times 10 to the 4th kilograms meters per second. Set that equal to the final momentum, which is 5 times 10 to the 3rd kilograms times v final. Divide through by 5 times 10 to the 3rd kilograms. And you've got the final velocity is 30,000 kilograms meters per second divided by 5,000 kilograms. that works out to 6 meters per second. So the final speed of these two cars moving off to the right now after collision is 6 meters per second. Now, does that answer make sense? Well, the fastest object was moving at 10 meters per second, and the slowest object was moving at 5 meters per second. So the fast object is going to speed up the slower object, and the slower object is going to slow down the faster object during collision, right? Okay, so it makes sense that the answer should be between 10 meters per second and 5 meters per second. No faster than 10, no slower than 5. Well, this falls in that category. But why isn't it exactly halfway between the two? Why isn't it exactly 7.5 meters per second, halfway between 10 and 5? Well, one of the cars is much more massive than the other car. So doesn't it make sense that the collision would have less effect on the speed on the change in speed of the more massive car than on the less massive car? That's exactly what happened. The more massive car is 4 times as massive as the less massive car, and its change in speed was 1/4 as great as the change in speed of the less massive car, right? So there we found the final velocity. Now I'm going to find the change in momentum of each car. So for car A, that's the one on the left, its change in momentum is going to be equal to the final momentum minus the initial. That's going to be 6,000 kilograms meters per second minus 10,000 kilograms meters per second, which is negative 4,000 kilograms meters per second. So 4,000 kilograms meters per second of momentum drained out of the faster car during the collision. And if you do the same calculation for the car on the right, car B, its change in momentum is going to be 24,000 minus 20,000 kilograms meters per second, or positive 4,000 kilograms meters per second. So the change in momentum of the more massive car during the collision is positive 4,000 kilograms meters per second. The change in momentum of the less massive car is negative 4,000 kilograms meters per second. So basically what happened during this collision is that momentum drained from one object into the other, but none of it was lost if you consider both cars together. So momentum was transferred, but not lost during the collision. Now, what about the kinetic energy? Well, the potential energy hasn't changed, right? There's been no change in height of the object, so its gravitational potential energy can't change for either car. On the other hand, the kinetic energy of the system, of the two-car system before the collision, we can calculate, and the kinetic energy of the cars after the collision we can calculate. Let's see what we get if we do that. Okay, for case 1, the kinetic energy is going to have 2 terms because there's 2 things that are moving before the collision. So it's 1/2 times the mass times the velocity squared. Remember, that's going to be in joules for the first car, and then plus 1/2 times the mass times the velocity squared for the second car. And if you calculate that out, you get 10 to the 5th or 100,000 joules of kinetic energy for the 2 cars before the collision. Now let's calculate the kinetic energy after the collision. There's only one term because the 2 cars are moving off as one now, they're connected. So it's 1/2 times their combined mass, so 5 times 10 to the 3rd kilograms, times their final speed squared of 6 meters per second squared. And if you do that calculation, you get 90,000 joules. So if you do the change in kinetic energy, if you find the change in kinetic energy, it's the final minus the initial, and you get negative 100,000 joules. So 100,000 joules of energy was lost during this collision. Where did it go? Well, and by the way, so what we've got here is a case where the initial and the final momentum of the system are the same before and after collision, but the kinetic energies aren't the same. The final kinetic energy is 100,000 joules less than the initial. So this is called an inelastic collision when that happens. Now the question is, where did that energy go? Well, 100,000 joules of work were done by the cars on each other. Car 1 exerts a force through a distance on car 2. Car 2 exerts a force through a distance on car 1, doing permanent damage and removing some of the kinetic energy from the system. How much? 100,000 joules. So how much work is done by each car on the other in permanent deformation or permanent damage to the cars? 100,000 joules of work.